Welcome! In this session, we're diving into problem number 311, sparse matrix multiplication.
This problem is a great opportunity to explore efficient matrix operations, particularly when the inputs are sparse.
We'll analyze the brute force approach and discuss its trade-offs. Let's get started. This problem involves multiplying two sparse matrices, mat1 and mat2.
Sparse matrices are matrices where most of the elements are zero, and this characteristic can be leveraged to optimize the computation. In this case, mat1 has dimensions m by k, and mat2 has dimensions k by n.
The goal is to compute their product, which will result in a new matrix of dimensions m by n.
You can assume that the dimensions of the matrices are always compatible for multiplication, meaning the number of columns in mat1 equals the number of rows in mat2. The input consists of two 2D lists of integers representing these matrices, and the output will also be a 2D list representing the resulting matrix after multiplication.
Let's consider an example to clarify how this multiplication works.
In the first example, mat1 is a 2 by 3 matrix, and mat2 is a 3 by 3 matrix.
When we multiply them, the result is a 2 by 3 matrix.
To calculate each element of the resulting matrix, we take the dot product of the corresponding row from mat1 and column from mat2. For the first row of mat1, 1, 0, 0, we multiply it with each column of mat2. For instance, the first column of mat2, 7, 0, 0, gives the dot product 1 by 7 plus 0 asterisk 0 plus 0 asterisk 0, which equals 7. Similarly, the second and third columns result in 0. This forms the first row, 7, 0, 0. For the second row of mat1, 1, 0, 3, we repeat the process. Multiplying it with the first column of mat2 gives 1 asterisk 7 plus 0 asterisk 0 plus 3 asterisk 0, which equals minus 7. The other columns result in 0 and 3, forming the second row, 7, 0, 3. The final matrix is 7, 0, 0, 7, 0, 3.
In the second example, both input matrices are zero matrices.
mat1 is a 2 by 3 matrix filled with zeros, and mat2 is a 3 by 2 matrix also filled with zeros. When multiplying these matrices, every dot product involves only zeros, so all the resulting elements in the output matrix are zero as well. The result is a 2 by 2 zero matrix, 0, 0, 0, 0. This example highlights a key property of sparse matrices. When one or both of the matrices are zero matrices, the output is guaranteed to be a zero matrix of the appropriate dimensions. In the third example, mat1 is a 1 by 3 matrix, and mat2 is a 3 by 1 matrix. The multiplication involves taking the single row from mat1, 1, 2, 3, and the single column from mat2, 4, 5, 6. The dot product is calculated as 1 by 4 plus 2 by 5 plus 3 by 6, which equals 32. Since there's only one row in mat1 and one column in mat2, the result is a single element matrix, 32.
This example demonstrates how matrix multiplication works even when one or both matrices are effectively vectors. Finally, there are some constraints and edge cases to consider.
Both matrices have dimensions capped at 100, meaning their size cannot exceed 100 by 100. The values in the matrices range from -100 to 100, and both matrices are sparse, meaning that most of their elements will be zeros. Important edge cases include scenarios where one or both matrices are entirely zeros, resulting in a zero matrix output, cases where the dimensions are such that one matrix is a row or column vector, and situations involving very large matrices with a high proportion of zeros. Addressing these edge cases and leveraging the sparsity of the matrices is crucial for optimizing the solution.
To begin, let's consider two different approaches to solving the sparse matrix multiplication problem. The first is the brute force approach, where we directly apply the standard matrix multiplication formula. For each element in the resulting matrix, we compute the dot product of a row from mat1 and a column from mat2. While this method is simple and intuitive, its time complexity is m asterisk k asterisk n, where m is the number of rows in mat1, k is the number of columns in mat1, or rows in mat2, and n is the number of columns in mat2. This works fine for dense matrices, but it becomes highly inefficient for sparse matrices, which contain a significant number of zeros. Since multiplying by zero doesn't contribute to the result, this approach ends up wasting a lot of computational effort on redundant calculations. To address this inefficiency, we can turn to an optimized approach that leverages the sparsity of the matrices. By skipping over 0 elements in both matrices, we can avoid unnecessary computations. For instance, if a particular element in mat1 is 0, it doesn't contribute to any dot product. Similarly, if an element in mat2 is 0, it has no impact on the resulting matrix. This insight forms the basis for a more efficient solution. Now, focusing on the optimized sparse approach, the key is to represent the matrices in a format that allows us to directly access only the non-zero elements. One effective way to do this is by using a dictionary or a list of tuples to store the non-zero values alongside their indices. With this representation, we can iterate only over the non-zero elements in mat1 and, for each of these, compute their contribution to the relevant positions in the result matrix by interacting only with the corresponding non-zero elements in mat2. This drastically reduces the number of operations, as we no longer touch the zero values at all. As a result, the time complexity depends on the number of non-zero elements in the matrices rather than their total size, which is approximately O, nz1 asterisk nz2, where nz1 and nz2 are the counts of non-zero elements in mat1 and mat2, respectively. This makes the optimized sparse approach significantly more efficient for sparse matrices. The rationale behind choosing this strategy lies in its ability to reduce computational overhead and memory usage by focusing only on the values that matter. By avoiding unnecessary iterations over 0 elements, we can solve the problem much faster and with fewer resources compared to the brute force method. To compare the two approaches, let's weigh their trade-offs. The brute force method is undoubtedly simpler and quicker to implement, which is one of its key advantages. However, it is computationally expensive for sparse matrices, as it performs redundant operations involving zeros. On the other hand, the optimized sparse approach is specifically tailored for sparse matrices. Its primary advantage is its efficiency, as it skips unnecessary computations and reduces the time complexity to depend only on the number of non-zero elements. However, this approach does require additional effort to pre-process the matrices, such as converting them into a format that efficiently stores non-zero values. While this adds some complexity to the implementation, the performance benefits far outweigh this minor drawback in scenarios involving sparse matrices. In summary, while the brute force approach is straightforward, the optimized sparse approach is the superior choice for this problem. By leveraging the sparsity of the matrices, we achieve substantial improvements in performance and resource usage, making it the most practical and efficient solution for this type of problem. In this problem, we aim to compute the product of two matrices, mat1 and mat2. The process of matrix multiplication involves taking the dot product of each row from mat1 with each column from mat2 to populate the resulting matrix, which we'll call result. Let's assume mat1 has dimensions mxk, and mat2 has dimensions kxn. The first step is to validate the input. For matrix multiplication to be possible, the number of columns in mat1 must match the number of rows in mat2, which is represented by k. If the dimensions don't align, we'll need to handle this error appropriately. Once we've verified this, the next step is to initialize the result matrix. This matrix will have dimensions mxn, corresponding to the rows of mat1 and the columns of mat2. It's initialized with zeros to ensure we have placeholders ready for each computed element. Using a 2D list in Python or a similar structure in other programming languages is typically the best approach. After initializing, we move on to the core computation of the product, which we'll explore in more detail next. To compute the product, we start by iterating through each row of mat1. For each row, we then iterate through each column of mat2. The key operation is to calculate the dot product of the current row from mat1 with the current column from mat2. The formula for this is result I j equals sum mat1 I p asterisk mat2 p j for p in range k. Essentially, for each element in the row of mat1, we multiply it with the corresponding element in the column of mat2 and sum these products to obtain a single value. This value is then stored in the appropriate position in the result matrix at result I j. Once all rows and columns have been processed, the result matrix, which now contains the product of the two matrices, is returned. Now, let's consider some key insights about the algorithm. The time complexity is determined by the three nested loops, one over the m rows of mat1, a second over the n columns of mat2,
and a third over the k elements for the dot product computation. This results in a time complexity of O, m*n*k. For space complexity, the main requirement is the result matrix, which has dimensions mxn, giving a space complexity of O, m*n*. However, we can optimize this approach for sparse matrices by skipping computations that involve zero elements, significantly reducing the number of operations in cases where the matrices contain many zeros.
To efficiently implement this algorithm, we use simple data structures. Both mat1 and mat2, the input matrices, are represented as 2D lists or arrays. The result matrix is also a 2D list initialized with zeros to store the final product. It's important to handle edge cases to ensure the algorithm is robust. For instance, if the dimensions of mat1 and mat2 are incompatible, we should return an error or handle the case gracefully. If either of the input matrices is empty, the result should also be an empty matrix. Sparse matrices provide an opportunity for further optimization. By skipping computations involving zero elements in the rows or columns, we can avoid unnecessary operations. To better understand the algorithm, let's walk through an example. Suppose mat1 is a 2 by 3 matrix and mat2 is a 3 by 2 matrix. The result matrix will be initialized as a 2 by 2 matrix of zeros, ready to store the computed values. In this example, for the first row of mat1, we compute the values for each column of mat2. For result 0, 0, we calculate 1 by 7 plus 2 by 9 plus 3 by 11, which equals 58. For result 0, 1, the calculation is 1 by 8 plus 2 by 10 plus 3 by 12, which equals 64. Moving to the second row of mat1, we compute the corresponding values. For result 1, 0, we calculate 4 by 7 plus 5 by 9 plus 6 by 11, which equals 139. Similarly, for result 1, 1, the calculation is 4 by 8 plus 5 by 10 plus 6 by 12, which equals 154. Once all rows and columns are processed, the final result matrix is 58, 64, 139, 154. This example highlights how the dot product formula is applied systematically to populate the result matrix. By addressing edge cases and taking advantage of optimizations like skipping zero computations in sparse matrices, this approach can be further refined for real-world applications. Here, we begin by defining a class called solution and implementing the multiply method, which performs sparse matrix multiplication. First, we determine the dimensions of the input matrices, mat1 and mat2. This involves extracting the number of rows and columns for each matrix. Since matrix multiplication requires the number of columns in the first matrix to match the number of rows in the second, we validate this condition. If the dimensions are incompatible, we simply return an empty list as the result. Next, we initialize a result matrix filled with zeros. The size of this matrix is determined by the number of rows in mat1 and the number of columns in mat2, as these define the dimensions of the output. To optimize the multiplication process, we create a dictionary called mat1_non0 to store the non-zero elements of mat1. This dictionary maps row indices to a list of tuples, where each tuple represents the column index and the value of a non-zero element. By iterating through mat1, we populate this dictionary, ensuring that we only process non-zero elements, which is crucial for sparse matrix efficiency. Once we have the non-zero elements of mat1 stored, we proceed with the multiplication. For each row in the mat1_non0 dictionary, we retrieve its list of non-zero elements. Each element provides the column index and its value, which we use to find the corresponding row in mat2. We then iterate through all columns of mat2 and perform the multiplication only if the current element in mat2 is non-zero. The product of the values from mat1 and mat2 is added to the appropriate position in the result matrix. This approach ensures that we skip unnecessary computations involving zeros. Finally, after completing the nested loops, the fully populated result matrix is returned as the output. This implementation effectively leverages the sparse nature of the input matrices, minimizing redundant operations and improving performance. Here, we begin the Java implementation of sparse matrix multiplication. First, we import the necessary utilities and define our solution class. Inside the multiply method, we take two input matrices, mat1 and mat2.
The initial step is to determine their dimensions m and k for mat1, and k2 and n for mat2. For matrix multiplication to be valid, the number of columns in mat1, denoted by k, must match the number of rows in mat2, k2. If this condition is not met, we return an empty matrix. Next, we initialize the result matrix with dimensions m by n, filled with zeros, which will store the product of the two matrices. Since this is a sparse matrix multiplication, we need an efficient way to handle non-zero values. To achieve this, we use a hash map called mat1 non-zero, where each key represents a row in mat1. The value is a list of integer arrays, with each array storing the column index and the corresponding non-zero value at that position. We then populate this map by iterating through mat1, adding entries for all non-zero elements. This helps us focus only on the significant values, improving performance. Now, we perform the actual sparse matrix multiplication using the data stored in mat1 non-zero. For each row in mat1 that contains non-zero elements, we retrieve its corresponding list of column indices and values. For each pair in this list, we extract the column index, j, and the associated value, val1. Then, we iterate over all columns in mat2's current row, checking if the element at position mat2, j, col, is non-zero. If it is, we calculate the product of val1 and mat2, j, col, and add it to the corresponding position in the result matrix. This approach effectively skips unnecessary calculations involving zero values, making the algorithm efficient for sparse matrices. Finally, once all relevant computations are complete, we return the result matrix, which contains the product of mat1 and mat2. Let's begin with the first example, which demonstrates a basic case of sparse matrix multiplication. Here, we have two matrices, mat1 and mat2. The first step is to initialize the dimensions and the result matrix. The dimensions are extracted as m equals 2, k equals 3, k2 equals 3, and n equals 3, and the result matrix is initialized as a zero matrix of size mxn, which is 0, 0, 0, 0, 0, 0. Next, we optimize our computation by identifying the non-zero elements in mat1. We store these in a dictionary called mat1_non-zero, where each row of mat1 is mapped to its non-zero elements. For example, in row 0, there is one non-zero value, 1, at column 0, so we store 0, 1. In row 1, there are two non-zero values, -1 at column 0 and 3 at column 2, so we store 0, -1, 2, 3. This step helps us skip unnecessary operations on zero elements during the multiplication process. Now that we've identified the non-zero elements in mat1, we proceed to the multiplication step. For the first row, I equals 0, the only non-zero element is 0, 1. We multiply this with the corresponding row in mat2. Specifically, column 0 of mat1 interacts with row 0 of mat2. This leads to the computation result, 0, 0, plus equals 1 asterisk 7, which updates the first element of the result matrix to 7. For the second row, I equals 1, there are two non-zero elements, 0, -1, and 2, 3. Starting with 0, -1, we multiply it with row 0 of mat2, resulting in result, 1, 0, plus equals -1 asterisk 7, which updates the value to -7. Then, 2, 3, is multiplied with row 2 of mat2, yielding result, 1, 2, plus equals 3 asterisk 1, which updates the last element of the row to 3. The final result matrix after these computations is 7, 0, 0, -7, 0, 3. This completes the first example, showing how sparse matrix multiplication reduces unnecessary calculations. In the next example, we work with larger matrices to further illustrate sparse multiplication. The input matrices, mat1 and mat2, are of sizes 3 by 3 and 3 by 2, respectively. We start by initializing the result matrix as a zero matrix of size 3x2, which is 0, 0, 0, 0, 0, 0. Next, we identify the non-zero elements in mat1 and store them in mat1_non-zero. For row 0, the only non-zero value is 2 at column 1, so we store 1, 2. Row 2 has two non-zero values, 3 at column 0 and 4 at column 2, so we store 0, 3, 2, 4. With this mapping, we move to the multiplication step. For row 0, the non-zero element, 1, 2, interacts with row 1 of mat2, specifically column 1 of mat1 with row 1 of mat2. This computation is result 0, 0, plus equals 2 asterisk 6, updating the first element of the result matrix to 12. Continuing with the multiplication process, we now handle row 2 of mat1, which contains two non-zero elements, 0, 3, and 2, 4. The first, 0, 3, interacts with row 0 of mat2, specifically column 0 of mat1 with row 0 of mat2. This results in the computation result 2, 1, plus equals 3 asterisk 5, which updates the second element of the last row to 15. The second non-zero element, 2, 4, interacts with row 2 of mat2, specifically column 2 of mat1 with row 2 of mat2. This leads to result 2, 1, plus equals 4 asterisk 7, adding 28 to the existing value and updating the element to 43. After completing these steps, the final result matrix for this example is 12, 0, 0, 0, 0, 43. This demonstrates how sparse multiplication efficiently handles larger matrices by focusing only on non-zero entries. Finally, we look at an edge case where both matrices are entirely zero. Here, mat1 is a 2 by 3 matrix and mat2 is a 3 by 2 matrix, both filled with zeros. As always, we start by initializing the result matrix as a zero matrix of size 2x2, which is 0, 0, 0, 0. Next, we attempt to build mat1 underscore non-zero to identify non-zero elements in mat1. However, since all elements in mat1 are 0, mat1 underscore non-zero remains an empty dictionary. Without any non-zero elements to process, no multiplication is performed, and the result matrix remains as 0, 0, 0, 0. This case highlights that when both matrices are sparse with no non-zero entries, the resulting product is also a zero matrix, demonstrating the efficiency of skipping unnecessary calculations entirely.
To analyze the time complexity of our sparse matrix multiplication algorithm, we begin with the initialization of the result matrix.
The result matrix has dimensions m by n, and initializing it with all zeros takes m asterisk n time.
Next, we process the non-zero elements of the first matrix, mat1.
Since mat1 is an m by k matrix, iterating over all of its elements to locate and store the non-zero values in a dictionary will take m asterisk k time in the worst case, where all elements are non-zero. However, in the best case, if the matrix is completely sparse, this step would be much faster, potentially taking 1 time as there would be no non-zero elements to process. This step ensures we efficiently capture the sparsity of mat1 before proceeding to the multiplication phase. Now let's consider the multiplication step, where the actual sparse matrix multiplication takes place. For every non-zero element identified in mat1, which we call nz1, we iterate over the corresponding non-zero elements in mat2. Let's denote the number of non-zero elements in mat2 as nz2. For each non-zero value in mat2, we update the corresponding entry in the result matrix. This means the time complexity here depends on both nz1 and the number of columns in mat2, giving us nz1 asterisk n. In the worst case, where both matrices are dense and contain no sparsity, the operation degenerates to m asterisk k asterisk n. However, for sparse matrices, the time complexity is significantly reduced to nz1 asterisk n, making the algorithm more efficient for inputs with a high degree of sparsity.
Next, let's evaluate the space complexity of the algorithm.
The result matrix, with its dimensions of m by n, requires m asterisk n space for storage.
In addition, we store the non-zero elements of mat1 in a dictionary called mat1 underscore non-zero.
This dictionary holds nz1 entries, where each entry requires space for the column index and the value itself, resulting in nz1 space. Combining these two, the overall space complexity becomes m asterisk n plus nz1. In the worst-case scenario, where the matrices are dense, nz1 would equal m multiplied by k, making the space complexity m asterisk n plus m asterisk k. For sparse matrices, the space complexity is dominated by m asterisk n plus nz1, which is significantly smaller than the dense case and aligns well with the optimization goals of the algorithm. When comparing this optimized approach to the brute force method, the advantages become clear. The naive brute force approach iterates over every element of mat1 and mat2, performing all possible multiplications and additions regardless of the presence of zeros, leading to a time complexity of m asterisk k asterisk n. This approach does not account for sparsity, wasting computational resources on redundant operations involving zero values.
In contrast, the optimized solution intelligently leverages the sparsity of the matrices.
By focusing only on the non-zero elements, it avoids unnecessary computations, reducing the time complexity to O, nz1*n for sparse matrices. This improvement is particularly impactful when working with highly sparse inputs, as it significantly enhances computational efficiency compared to the brute force method.
Finally, let's break down the best, average, and worst-case scenarios for the algorithm. In the best case, both matrices are completely sparse, meaning they have very few non-zero elements.
Here, the time complexity is O, nz1*n, where nz1 is much smaller than m multiplied by k. In the average case, the matrices are partially sparse, and the time complexity remains O, nz1*n, with nz1 depending on the actual sparsity of mat1. In the worst case, the matrices are dense and contain no sparsity, causing the algorithm to revert to the same time complexity as the brute force approach, which is O, m*k*n. This variability highlights the efficiency gains of the optimized solution, especially when dealing with sparse data, while acknowledging that its performance aligns with traditional methods when sparsity is absent. When working on sparse matrix multiplication, there are some common mistakes to watch out for.
First, many people overlook edge cases, such as when one of the matrices is empty or when the dimensions of the two matrices are incompatible for multiplication.
To prevent this, always validate your inputs, ensure that the number of columns in the first matrix matches the number of rows in the second.
Another mistake is hard-coding the matrix dimensions into your solution.
Instead, use dynamic values like the length of the matrix or its rows and columns to ensure your code works for any valid input size. Inefficient use of nested loops is another pitfall. Triple nested loops, without any optimization, can lead to timeouts when dealing with large matrices.
To address this, try leveraging the sparsity of the matrices or pre-computing reusable values to optimize the innermost loop.
Also, be careful with the dot product calculations. Mismatched indices are a frequent source of errors, so make sure you're iterating over the rows of the first matrix and the columns of the second correctly. Finally, when working with sparse matrices, storing all the zeros explicitly can lead to unnecessary memory overhead. A better approach is to use dictionaries or lists that store only the non-zero values, making your solution both space-efficient and faster to process. Matrix multiplication often shows up as a subproblem in areas like dynamic programming, graph algorithms, and machine learning. Recognizing this pattern can help you systematically approach related problems. For dense matrices, the naive approach has a time complexity of O, n cubed.
However, there are more advanced algorithms, like Strasson's, which can reduce this complexity to about O, n to the power of 2.81. Keep in mind, though, that these methods can be challenging to implement and aren't ideal for sparse matrices.
When working with sparse matrices, you can optimize to a time complexity proportional to the number of non-zero elements, which is often much faster.
During interviews, it's important to ask clarifying questions about the properties of the matrices. For example, are the matrices guaranteed to be sparse? Are there specific constraints you need to account for?
This information can help you tailor your solution and focus on the most effective approach.
Lastly, thorough testing is critical.
Make sure to test your code against edge cases, such as matrices with only one row, one column, or non-square dimensions, to ensure your solution is robust and handles all scenarios correctly. There are several related problems that you might encounter, such as LeetCode 54's spiral matrix, which involves traversing a matrix in a spiral order, or LeetCode 48's rotate image, which deals with rotating a square matrix in place. Another related problem is LeetCode 73's set matrix zeros, where you modify the matrix based on certain conditions.
Each of these problems offers a unique perspective on matrix manipulation.
When it comes to alternative approaches for matrix multiplication, one option is Strasson's algorithm, which reduces the time complexity to roughly O, n to the power of 2.81.
However, it's quite complex to implement and isn't well suited for sparse matrices.
For sparse matrices, focus on optimizing by working only with non-zero elements, using data structures like dictionaries or lists to store these values.
This reduces both time and space complexity significantly. Divide and conquer is another strategy where you break the matrices into submatrices and solve recursively. This approach can also be useful for parallel computing. Lastly, in real-world scenarios, leveraging optimized libraries like NumPy in Python or Eigen in C++ is often the most practical choice. These libraries are highly efficient and take care of the underlying complexities, allowing you to focus on the higher-level problem. Great job making it through. To sum up, we tackled problem number 311 and explored the brute force approach for sparse matrix multiplication. Remember, understanding sparsity is crucial for optimizing performance. Thanks for watching, be sure to practice, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!